All right. So we're going to start a new module today. Module 5 is on semiconductor junctions, otherwise known as a diode. We're going to talk about we'll start class by just reminding ourselves some of the features or applications of diodes, and then we'll get into the meat of the material. So this part of the class, from here on out, modules 5 and 6, and possibly 7, is going to take a slightly different approach than the previous modules. In the previous modules, we were focused on learning the fundamentals of semiconductor materials. So, learning the language of energy band diagrams, learning what carriers are, learning about the physics and how they move and things like that. So we're kind of like building up the language, building up the basics of understanding. So now we're going to switch and focus on devices. Okay, and what I would like you to think about is use these devices as a way to reinforce the fundamental concepts that you've learned in the first 3 modules. Okay, we're going to be talking about diodes in module 5, also metal semiconductor junctions, a little bit about photodiodes. Okay, because these are all different types of semiconductor junctions. And in module 6, we're going to talk about field effect transistors, the MOSFET. Okay, oh, I see we have a question here. Are the notes uploaded on Canvas? Yes, Jinan, they should be. If you're not able to see them, then let me correct that.
I don't see them. They're not showing up under my module.
You don't see them? Okay. I did upload them. Oh, you know what? Maybe I didn't make them visible. So let me just check that right now. Okay, just bear with me here for a minute. I must have not made it visible. Okay. There we go. All right, now you should be able to see it. And download it. Okay, sorry about that. Okay, so what was I saying? Semiconductor junctions and MOSFETs are the 2 different types of devices that we're going to be talking about. But as I told you earlier, like the world of semiconductors is always changing, it's always evolving. So the key thing that I want you to get out of a graduate level class like this is I want you to be able to apply the concepts of semiconductors, the concept of carrier statistics, energy band diagrams, and what have you, into ultimately into new devices that you'll be working on in your careers if you choose to go into this area. Okay, so we'll be taking a standard of approach. We'll talk about, we'll talk about energy band diagrams, we'll talk about physical models, and then we'll eventually derive equations that describe the device operations, the current voltage characteristics. Okay, so thus far, just to give you a little bit of context, what we're going to be talking about in this module. So far, we've learned about the properties of N-type and P-type semiconductors on their own. Right, so we did energy band diagrams, we did, we drew the carrier statistics, we talked about the physical structures, we derived some practical quantities, like we derived the resistance of the material, the conductivity. If we put a voltage across there, we saw that there'll be a current and there'll be, there'll be an associated resistance associated with that semiconductor. All right, so we've basically learned the basics, and we've also learned about one electronic device, and that is a resistor. In this module, we learn about a diode. A diode is created when a P-type and an N-type material are put together. Okay, conceptually put together. You don't make a diode by taking a P-type and N-type material and just squashing them together like this. There's actually because there would be too much, there would be air pockets in between them. So the way that it's made is a little bit different. But conceptually, I want you to think about a P-type and an N-type material right next to each other. Okay, now this might seem, in some ways it's an evolutionary type thing. We talked about P and N-type materials, and then now we're just putting them together and seeing what happens. So that's one way to think about what we're going to be learning about in this module. And then, that's the approach we're going to take. So we're going to talk about the energy band model first. We'll talk about the physical model together with the energy band model, and then we'll derive these equations that describing the device operation. And we'll derive the device operation and understand the energy band and physical models under different conditions. So we'll talk about the equilibrium. That's the focus for today. Remember equilibrium. Can anyone remind us what equilibrium is? Equilibrium versus steady state versus transient. What is equilibrium? So how did we define equilibrium from last module?
You have no net current, and the carrier concentrations don't change with time.
Yep, carrier concentrations don't change with time. How about specifically with stimulus? What does equilibrium mean in terms of stimulus?
We have no stimuli.
No stimulus. That's right. That's right. So no stimulus means there's no light being shined on the diode. There's no voltage being applied to the diode. It's just the diode on its own. So our focus today is on the equilibrium behavior, and we'll really get a deep understanding of what the carriers are doing, and then eventually we'll get into the forward and reverse bias when we apply voltages to the diode. Okay. And later on, we'll talk about photodiodes, which convert light into voltages and currents, and then we'll talk about metal semiconductor junctions. So just a quick preview. We're going to talk, this is a sort of an overview schematic of what the physical model is. We're going to talk about the drift and diffusion balance. We'll talk about something called the space charge region or depletion region that occurs right at the interface between the two materials. In the energy band model world, we're going to draw energy band diagrams for a PN junction. You'll see that there's a Fermi level that goes straight across like this, but there's this phenomena called band bending. Okay, so this is kind of a new tool in our energy band, in our understanding or our toolkit of energy band diagrams. So we're going to see how this phenomena of band bending occurs, and we'll talk about how we can calculate the built-in potential of the diode. And then eventually, as I said, we're going to talk about diode device equations at equilibrium, forward bias, reverse bias, and we'll talk a little bit about the transient behavior of the diode as well. So many of us have seen this symbol. This is a diode. Okay. You know, last module we talked about resistor. Draw that out. The most basic electronic component. And in this module, we talk about a diode. So a diode is an interesting element. It has an exponential IV characteristic. We'll talk about this a lot more in depth later, just giving you a bit of a preview here. In a diode, interestingly, the current voltage characteristic looks like this. This is for a diode. Whereas with the resistor, the current voltage characteristic is linear. I'll just put RES for resistor here. Okay. So you might think this is, well, that's kind of boring. This is just like IV characteristics. It turns out that having an exponential IV characteristic is really important in a lot of applications. I'll give you one application, then I want us to just think about like what are diodes used for, just because I want everyone to have an appreciation for the material that we're going to study today. Okay, so I'll give one example is that when you're doing resistors, you have a linear IV characteristic, and that's useful in a lot of sensor type applications. It's useful in designing filters like RC filters, low pass and high pass filters when you combine a resistor with a capacitor, for example. Diodes, because they have this exponential IV characteristic, turns out that exponential characteristic is really useful for mixers in RF communication circuits. okay, because the frequencies end up multiplying, and you get a lot of like very interesting effects that happen with the diode. So this characteristic is very important for radios, wireless radios. The other thing about the diode, if I just extend this out here like this, is that the diode doesn't conduct current in the reverse direction until you get to something called reverse breakdown. But that's something we'll just worry about later. With the resistor conducts current in both directions. You can have a current going this way. You can also have a current going this way. But when we often think about diodes, the current only goes in one direction. Okay, so that itself is a very useful property when you're designing circuits. There are a lot of, for example, electrostatic discharge circuits that utilize the fact that you can only have current going in one direction. Rectifier circuits, the things that are used in our wall chargers, they are based on like a half-wave rectifier has 2 diodes in it, a full-wave rectifier has 4 diodes in it. Don't worry about the details, but it's an important component in everyday chargers. Now, besides just as a circuit element, we're going to talk about photodiodes. Photodiodes convert light into current, into electrical current. Can anyone tell me where photodiodes are used and where they're useful?
Solar panels.
Solar panels, exactly. I mean, if we didn't have diodes, we would not have solar power. We would not have solar panels. A photodiode is the basis of a solar panel. Thank you, Janan. There's a few other ones that I think are worth mentioning, just to make sure we're all on the same page and appreciate the importance of the diode. Can anyone think of another possible application?
Infrared sensors.
Infrared sensors, yeah, absolutely. Infrared sensors are used in our TV remote controls. Infrared sensors are used in home security systems. If there's something else that was on your mind, Corey, that you were thinking about, please feel free to let us know. But those are the things that kind of come to mind.
I just always think of the thing you can trip on a garage door. They have like the little sensor that doesn't close on you.
Yep. Those types of sensors are proximity sensors. That's a type of security sensor as well. Nowadays, some types of proximity sensors are used for in automotive type applications for detecting how far a car is away from a wall. There's another really important one. I could create slides on this because it's very important. Fiber optic communications. The backbone of our internet runs on fiber optic communications. And the way that fiber optic communications work, if I can, there we go, just draw this out here. All right. Yeah, so some of you are, I'm sure, are familiar with fiber optic communications, but let's just say, here's the US, here's Europe. If some of you may or may not know that there's a whole track of undersea cables that goes underneath the Atlantic Ocean. Okay, and there's many optical fibers in those bundles. Okay, and that is really the basis of high-speed communications between US and Europe. As I don't know if I mentioned this on the first day of class, but these undersea cables are really important geopolitical elements, right? Because if you cut off communications, cut off high-speed internet between countries, there's a lot of bad things that could potentially happen. So these undersea cables are guarded. There's a lot of panic in the US government, I think, sometime last year or 2 years ago when they found that Russian subs were patrolling near the undersea cables. So just to give you a sense, the internet backbone is extremely important. And the way fiber optic communications work is you have laser diodes or LEDs, light emitting diodes. So these are both based on diodes. These send pulses of light in certain patterns down these fiber optic cables. And on the other side, so the symbol on this side is it's a diode. And when you pulse current through this diode, these diodes convert the current to light. And so they send pulses of light down this cable. And on the other side, you have a diode that's reverse biased that behaves as a photodiode. So this converts, so this is current to light. So you create pulses of light. And a photodiode converts light to current. And so, and by putting it through a resistor, you can retrieve your voltage. You can convert these light pulses into voltage pulses. And that's how communication works here. So without diodes, both generating the light and receiving the light, we wouldn't have fiber optic communications. This is really, really important application of diodes. And whenever we talk about semiconductors, I feel like MOSFETs always get the limelight. We always talk about Moore's law and like how we miniaturize the transistor through these radical new designs that enables us to do computation. All that is true, but the diode is an equally important element because it forms the basis of our fiber optic communications and light sensing and solar energy. So don't forget about the diode. Anyway, so let's, knowing that, now we can try to, we can appreciate the importance of the diode. Now we can talk about this from a more physical, scientific inquiry type perspective, okay? And the perspective I want you to take is, let's just skip over, this is a repeat slide, sorry. The perspective I want you to take is what happens if we put a P and an N-type material together, okay? This is a good exercise to do because it is, it's related to the things that you have discussed in your, it's related to the things that we have talked about in our previous modules, okay? 1 second here, let me fix my screen share here. I realize I'm probably projecting at the wrong resolution here, so I can fix that real quick. Okay. Are you all able to see that? Oh, wait, let me make sure I can share my screen again. Okay, are you all able to see the screen again now? Just give me a quick thumbs up if you're able. Okay, great. Okay, so getting back to the question, what happens if we put a P and an N-type material together? So we have an N-type material. Imagine that we have an N-type semiconductor here, and then we have a P-type semiconductor here. And I want to do this as an exercise. So I want you to think about the 4 mechanisms, the 4 carrier mechanisms that we talked about in the last module, and how would they apply to this type of situation where we have a P-type and an N-type material next to each other. Okay, so let's have someone in the class remind us what the 4 carrier processes are.
Generation, diffusion, drift, and recombination.
Excellent. Great. Thanks, Clayton. And whoever would like to take a stab at this. Suppose we put a p-type and an n-type material together. Which of those 4 carrier processes comes to mind first?
For me, the first is diffusion that comes to mind.
Okay, so why would diffusion happen?
So in the n-type material, kind of right at the interface, you would have not many holes, and then in the p-type, you wouldn't have many electrons. So
yeah,
you would kind of go kind of like a crisscross type of situation where the electrons will diffuse to the p-type, and then the holes will diffuse to the n-type.
Excellent. Yeah, great. So let me write that down here. So there's a high electron concentration in the n-type material. So electrons are going to diffuse this way. And there's a high concentration of holes in the p-type material. So the holes are going to diffuse this way. Why do they diffuse? Because remember, diffusion goes from high concentration to low concentration. So an n-type material has high electron concentration, p-type material has very low electron concentration. So the electrons will diffuse from high to low concentration. Similarly, with the holes from the p-type to n-type. So that's why, as Melvin said, it sets up this sort of crisscross type thing. Okay. Now I'm going to talk about some of the phenomena that happens on this slide, but I want to see if we can, let's just use this as a brainstorming session. So we know that diffusion is happening. What other phenomena might happen? What comes to mind here? And remember, anytime you're analyzing a new device that's put in front of you, you can start with these 4 processes. So diffusion happens because there's a concentration gradient. Let's go to drift. Can we think of any kind of thing that might cause drift? What causes drift?
Well, I guess if you place an electric field on the PN junction, then you would have drift of electrons,
right?
And drift of holes in opposite directions.
Right. Exactly. So at this point, we don't have an electric field yet because we haven't placed a voltage across the material. So we'll return to the drift in just a second. How about generation and recombination? What would enhance generation and what would enhance recombination?
Well, generation, if you had like something to heat it up.
Sure. Yep. If something's heated up, you'll have more generation. That's good. So in this case, I mean, let's say we're at equilibrium. So we're not heating up the material right now. So that temperature-based generation, let's put that aside for a second. But what other types of things might cause generation? There's light, I suppose. There's light. We're not shining light on the material, though. At any, even at room temperature, well, Janan pointed out, even at room temperature, there's some generation happening. Okay. Any other points we want to make about generation? Okay. So generation is happening. Recombination. Let's talk about recombination. What would enhance recombination? Just for review.
I guess the process of diffusion would lend itself to recombination.
The process of diffusion lends itself to recombination. Yes, that's a good point. And I think that this might seem a little bit confusing as to why to the rest of the class. So I want to back up for a second And first, just remind the class that recombination, if you want to enhance recombination, you would want to have more electrons, more holes. Okay, so whenever you have electrons and holes in close proximity to each other, there's a probability that they'll recombine. Okay, so one way to enhance recombination is just to have a high concentration of electrons and a high concentration of holes. But what do we have in the p-type material? Here, let me get my laser pointer out. Oh, that's weird. Okay, let me restart my PowerPoint here. Sorry, just bear with me for a second. All right, there we go. Okay, so we're at the point where we have a p-type, n-type material. So we're talking about why diffusion, why recombination may happen. Okay, so as the electron goes from the n-type material to a p-type material, now the electron sees a lot of holes on this side. Right? Whenever an electron encounters a hole, there's going to be a probability that it recombines. On the n side, there's a lot of electrons and very few holes. So while the electron happens to be on the n side, there's a lower probability that it'll recombine. But when it gets over to the p side, there's lots of holes. And so there's a greater probability that the electron will recombine. So we kind of think about that the electron is diffusing over to the other side and then it recombines. Okay, this is a simplistic way of thinking about it. The holes similarly diffuse over to the n-type material and then they recombine. Okay, so the diffusion and recombination are key processes that are happening here. And as we'll see, drift also plays a role. So now let's peel back another layer and look into a little bit more detail of what's going on here. So in order to do this, let's look closely at the molecular structures or the atomic structures. All right, and what do we see here? This is an n-type material. So in an n-type material, we kind of have this mental model in our heads that you have silicon atoms. It's mostly silicon atoms, but every so often there is a column 5 dopant, an arsenic, for example, or phosphorus. Okay, column 5 element donates an extra electron to the lattice. So each one of these sticks represents a complete bond. And then there's this additional electron that is created. Okay, and when that this electron is mobile, it's free to move around, it leaves behind an effective positive charge, right? We call this dopant ions because the nucleus of the dopant atom has an effective positive charge, right? When the electron happens to be nearby, these two are neutralized. But if the electron leaves, now you have a situation where you have one more proton in the nucleus than you have electrons nearby. So there's an effective positive charge here. Okay, so that's just a review. And the p-type material, we have 3 complete bonds and 1 incomplete bond. And that is what we refer to as a hole. And this has an effective positive charge. Kind of opposite the n-type material, the boron nucleus has an effective -1 charge when the hole moves away. All right. So, so we had our simplistic model up here where we said the electrons diffuse over to the other side and then they recombine. And so we're just going to illustrate that here. The electrons on the n-type material, they move from high to low concentration. Okay, so you imagine the electron diffusing over into the p side, and then at some point, so it diffuses over, but once it gets over to the p side, there's so many holes. Oh, we have a, okay, no problem. Once it moves over to the p side, there's so many holes here that there's a high probability that this electron is going to recombine. And so that we can kind of think about in our heads that, okay, once it gets over to this side, there's going to be recombination here. Similarly, when the hole sees this concentration gradient, high concentration of holes on the p side, low concentration on the n side, the holes also diffuse over. Okay, so imagine the hole moving away here like this. And then the hole sees a lot of electrons, and of course that also recombines. Any questions so far? All right, good. All right, so at this point, now something interesting happens. Notice that we have an effective positive charge here and an effective negative charge here. Okay, we've only drawn one, like one effective positive charge and one effective negative charge, but this is just for illustrative purposes. There's many electrons that are diffusing over and recombining, many holes that are diffusing over and recombining. So imagine that you have many of these positively charged dopant ions on the n side and many of these negative charged dopant ions on the p side. So what that's going to do, if we kind of remind ourselves, there's this concept in that we talked about in module 2, the concept of a capacitor. We often draw this as a very, we draw this in physics and electronics a lot. If you put a voltage across two metal plates like this, you end up getting a buildup of positive charge on one end of the plate, and then you end up getting an equal and opposite charge on the other side of the plate. So however many positive ions we have on this side, we have the same number of negative ions on this side. And we say Q, the amount of charge is equal to the capacitance times the voltage. Okay, so this is a basic capacitor, okay? But this concept, if you remember, we also talked about electric fields. In a capacitor, there is an electric field that's generated, that an electric field always goes from positive charge to negative charge. It points from positive to negative charge. Okay, and the relationship between voltage and electric field was E is equal to V over D, where D is the distance between the two plates. Okay, so that's a capacitor, but there's this fundamental idea in electromagnetics that whenever you create an electric field, there's an equal amount of positive charge as there is negative charge. Okay, and even more fundamental than that, whenever you have positive charges and negative charges next to each other, you get an electric field. All right, so what's happening in the PN junction is a classic capacitor-like situation where you're building up some positive and negative charge. Okay, so this has an effective positive charge, this has an effective negative charge. Which way is the electric field going to point?
To the right. Opposite of the electrons.
Oh, I see what you're saying. Yeah. So this is tricky because it actually, when we look at the electric field, we no longer look at what these electrons and holes are doing here. We're actually looking at the electric field set up by the dopant ions. So this is a subtle but important point. So I'm glad you brought that up. if you look at the dopant ions, this is positively charged and this is negatively charged. Which direction would the electric field then point? Janan, you want to take another stab at it?
Well, if it's not right, it's left.
Yeah. Yes. Good point. So yeah, there is an electric field that forms in this region here. Okay, and that electric field points from right to left. Okay, the electric field points from positive charge to negative charge. So Janan brought up a good point here. So she said that, well, the electrons are moving from right to left. So doesn't that mean that the electric field is pointing from left to right? And it actually isn't, because the electrons are moving by diffusion. They're not moving due to drift. If they were moving due to drift, then yes, then the electric field would point in the other direction. But that's the interesting thing about a PN junction, is that there is a combination of both drift and diffusion currents, as we'll find out. Okay, the diffusion currents, the electrons move to the left, the holes move to the right. They set up, when they move away, they leave behind these immobile dopant ions. Okay, that's a key difference between the electrons in the holes and then this boron ion and the arsenic ion. Okay, these things are stuck. They are bound to the lattice. The electrons and holes are free to move, but these ions are not, because they're covalently bound. Okay, so that's why we often talk about these things as immobile or static charges. Both terms are used. Immobile means it can't move. Static means it's not moving. So they're both the same definition. And in this type of capacitor-like situation, these charges are not moving. Okay, they build up on the plate, but then they stay on the plate. Okay. So that is what's happening here. These immobile charges are the ones that are creating this electric field. Just like here, when you put a voltage and you generate these positive charges and negative charges here. So you use the voltage to generate the positive and negative charges in this case, and you get an electric field resulting from that. In the PN junction, what happens is that the diffusion of electrons from left to right, the diffusion from holes, the diffusion of electrons from right to left, the diffusion of holes from left to right create these positive and negative charges. And those positive and negative charges generate this electric field. Okay. So because this region here, just at the interface between the N and P-type materials, is depleted of electrons and holes, we call it the depletion region. There's a second name for it. Because these are space charges, it's the depletion region is also sometimes called the space charge region. Both are interchangeable. Okay. So what's interesting is that this electric field is created, and so now we have to think about, well, there's drift current now, right? Because diffusion currents are caused by a concentration gradient. We've established that there's diffusion, but because of the diffusion, it left behind the depletion region, which has an electric field, and this electric field now creates drift current. All right, so now we have three important carrier processes that we have to think about in the PN junction. Generation is happening too, but it's we focus on these three processes. So if there's electric field, then there's going to be some movement of electrons back this way due to drift. And there's going to be some movement of holes back this way due to diffusion. I'm sorry, drift. Okay, electrons drift opposite the electric field. holes drift in the same direction as the electric field. All right, so these processes up here were diffusion. So the electrons are diffusing this way. And they're diffusing from right to left, drifting from left to right. And then the holes are drifting from right to left and diffusing from left to right. Okay. Turns out at equilibrium, the drift and diffusion currents, they balance each other and then they add up to zero. Okay, and that brings us back to the point that Janan made earlier, is that at equilibrium, the currents add up to zero. Okay. All right, so this is another way to look at it, another mental picture you can have in your head. You start off with a p-type semiconductor and an n-type semiconductor. Let's say, in a hypothetical thought experiment, if you put them together, the initial distribution would look like this. The electrons would start to diffuse over this way. The holes would diffuse over this way. And when they do that, they leave behind this depletion region, space charge region. Okay, you can see the holes have sort of diffused over to this side, and then they start to recombine because there's so many electrons here. The holes will find an electron and recombine. Similarly, the electrons diffuse over to the left side where there's a lot of holes, and they also will recombine. All right. So this idea here is kind of similar to what we talked about in module 4 with the concept of carrier injection. You're taking a carrier of one type and injecting it into the other side. In this case, the injection is happening by through diffusion. Okay, whereas in the last module, we were injecting carriers by shining light on it. Here, it's just happening just by the virtue of diffusion. Okay, but things diffuse over and then they recombine. This we'll get to the details of that later, but I want to remind everyone that the diffusion length is one of the things that we think about, when we talk about this type of phenomenon. All right. So this depletion region has an electric field associated with it. These are effective positive charges shown in red. These are effective negative charges shown in black. And so the electric field points from right to left. All right, so now we have a situation where there's a concentration gradient causing diffusion. There's an electric field causing drift. So just as a quick exercise, just to test our understanding of this, let's put in arrows here for the diffusion current and drift current. Okay, so I'd like everybody just take a couple minutes to do that. So in each one of these boxes, I would like you to indicate the direction of the current, not the flux, the current. So I'll just specify that here. Current. Which direction is the electron drift current? Which direction is the electron diffusion current? And the same thing for the whole drift and diffusion. Okay, so go ahead and try that. Take a few minutes, and we'll pick up in 2 minutes. All right. Any thoughts? So starting with the electron, let's start with electron drift.
Right to left.
Right to left. Let's see. Right to left. Yep, that's correct. And oh, sorry about that. There we go. So just Ali, what's just to make sure, what's your rationale behind that?
Because it's due to drift, so we need to consider the direction of the movement of electrons.
Right. Yep. So which way are the electrons moving? No, which direction is the flux?
From left to right.
Correct. Correct. Electrons are drifting from left to right, so the corresponding current is right to left. Excellent. Thank you, Ali. And how about the diffusion of electrons? Which direction is the electron diffusion current? Can I have someone else?
Would it be left to right?
Yep, you got it. So you can see from up here that the electrons, the flux of the electron diffusion is right to left. So they're going from the N side to the P side. So the corresponding current is left to right. And so what you notice here, this is interesting, right? This is, now you see that the drift current is moving in one direction and the diffusion current is moving in the opposite direction. Okay. And it turns out that the drift and diffusion currents at equilibrium are equal to each other. So Jn diffusion plus Jn drift are going to sum up to 0. So these arrows are going to be equal and opposite. All right, how about the holes? Which direction are the holes drifting?
It should be in the opposite direction as the electrons, so left to right.
Right? So
Or,
you're right that the movement, if you're talking about the movement of holes, they are moving from right to left, but the corresponding, I'm sorry.
I think
yeah, I think we're, go ahead.
Yeah, I think I got tripped up on this actually the last time we spoke about this. Yeah, I think that was also right to left.
Yeah, there you go.
Yeah, sorry.
Yeah, no, it's all good, all good. So when we're talking about drift currents, the easy way to remember it is whichever way the electric field is pointing, the drift currents are going to be the same, regardless whether electrons or holes, it doesn't matter. The currents always are in the same direction as the electric field. The holes are moving from right to left, and the corresponding current is also right to left. The electrons are moving from left to right, but the corresponding current is still right to left. Okay, and I'll just fill this one here real quick. The diffusion currents, the holes are diffusing from P type to N type, so they're going from left to right. The corresponding current is also left to right. Okay, just like before, you have drift currents to the left, diffusion currents going towards the right, and they are equal and opposite each other. They add up to 0 at equilibrium. Right, so once this equilibrium is established, the drift and diffusion currents balance each other, then the net current is 0. If the net current were not 0, that would be great because we'd have an infinite source of electrical energy. Unfortunately, you know, the laws of physics won't allow that to happen. Okay, but it's really cool that you end up getting these current components, but they just happen to balance each other out at equilibrium. All right, so now that we've looked at the physical model, let's talk about the energy band model. So at this point, what we're going to do is we're going to use these devices. We're going to use the diode as a way to expand our understanding of energy band diagrams. And what I mean by that is that I would like for all of you to kind of have a rule book, if you will, a set of rules that is used to a set of rules that you can use to draw energy band diagrams. Okay, so one of the first rules I'd like to put out here is that at equilibrium, no discontinuity or slope can appear in the Fermi level. No discontinuity or slope can appear at the Fermi level at equilibrium. Okay, so if you think about why this happens, it has to do with like carrier statistics. If you, last, 2 modules ago, we talked about what happens when you put voltage on one side versus the other. The Fermi levels, the Fermi level tilts. Okay, but at equilibrium, there's no voltage applied, so the Fermi levels are actually at the same point. The potential energies of the electrons are the same. The distribution of potential energies is the same regardless of where you are in the semiconductor. So that's why the no discontinuity or slope can appear at equilibrium. So it's just a flat line. Okay. Now the second rule is that there's a phenomenon called band bending that occurs in semiconductors. Okay, so I'll just explain really quick what that looks like. You have a p-type and an n-type material. We've already drawn these many times, so you know what the energy band diagram for a p-type material looks like. You have the Fermi level below the intrinsic level, so it's closer to the valence band. In an n-type material, you have your Fermi level close to the conduction band. Okay, so this is what they would look like on their own if they were not put into contact with each other. If they were in direct contact with each other, then what would happen is that these Fermi levels actually end up equalizing. Okay, so you imagine these, imagine the right side here, the n-type material, the Fermi level sort of coming down, or alternatively, you can think about the p side, sort of the whole side going up. Okay, but they move as a unit. Okay, that's something to keep in mind when you're working with these band diagrams. When these bands move, they move together. Why? Because think about that. This is still a p-type semiconductor, right? So out in this region, there's interesting things that happen in the middle here, but out here, this is just still a p-type semiconductor. So if it's a p-type semiconductor, the Fermi level has to be close to the valence band. It's still silicon, so you still have a band gap of 1.12 electron volts between EC and EV. The band gap could be different depending on what materials you have, but the point is like that you still have to maintain this band structure in a semiconductor material. Okay, so when the bands move, they move together. Okay, so when you align these two, you align the two diagrams together, and then after contact, these bands bend around like this. Okay, and so I'll just have a little bit more detail on that so you can know very specifically how to draw an energy band diagram for a p-n junction. Okay, so you start with a p-type material and then an n-type material. So the first step is to draw the Fermi level. And remember the rule that equilibrium, no discontinuity or slope can appear. So you start by drawing the Fermi level as a flat line like this. Okay. The next step is that you draw the p-type material on the left side. So you're going to draw the band diagram for this portion. And you already know how to draw band diagrams for p-type semiconductors and n-type semiconductors. The distance between EF and the intrinsic level and the conduction and valence band all depends on doping. The doping and the band gap both. Okay, so based on the type of semiconductor you have, the doping level you have, whether it's what doping concentration you have, you will position the valence band and the conduction band accordingly. So the Fermi level is going to be at some distance below EI, and that distance depends on your doping, so you know how to figure that out. So that will give you where your intrinsic level is. from where your intrinsic level is, you can position EC and EV, and the distance between those depends on the band gap. Okay, so based on the doping, you can basically draw this entire band diagram on the left side. Same thing on the right side, based on the doping. Based on the doping, the Fermi level will be positioned so many electron volts, some number of electron volts above EI. This distance will increase the higher the doping is. And again, the distance between EC, EI, and EV all depends on the band gap. So after you've drawn the individual components, in the middle at the interface, what you do is you connect the bands together. The conduction band can be connected like so, the valence band, and even the intrinsic band can be conducted like this. Just like that. Okay. Now, this connection here, you might seem like, well, this seems kind of arbitrary. How can we just connect the lines like that? But when we start looking at the mechanisms, I hope that this will actually start to make sense why we do it this way. Okay. I just want to put a few points out there right now that I hope that that might, give you some indication as to why. In the middle here is a depletion region. In the depletion region, there is very low electron concentration, very low hole concentration. There's just the dopant ions. So in the middle here, this is neither p-type nor n-type. It starts to look more like an intrinsic semiconductor. So in an intrinsic semiconductor, the Fermi level is right at the intrinsic level. So you see here how EF and EI cross together here. Okay, this is happening at the interface because right at the interface, you essentially have like an intrinsic type semiconductor. So this region here represents a transition from a p-type to an n-type semiconductor. The second thing is, like, whenever you have a slope in EC or EV, that means that there's an electric field. So initially, when you first see this, it may not make sense why it curves down like this, but we'll talk about different phenomena, and hopefully it'll start to feel more intuitive. So once we have this energy band diagram, we can think about sort of analyzing it. What are the different things that an energy band diagram tells you? So the first rule, the slope of a band diagram is proportional to the electric field. Okay, it's a rule to remember. So out in the p-type material out here, there's no slope in the band diagram, so there's no electric field here. Same thing with the n-type material. But at the interface we just talked about, there is an electric field right at the interface. Okay, so that is exactly where the slope in this band diagram occurs. Okay, is this a positive or negative slope?
Negative.
It's a negative slope, right? So in this case, it's a negative slope. So therefore, the electric field is proportional to the slope. So therefore, the electric field is negative. Negative means it points from right to left.
Hey, Professor.
Yeah.
I have a question for you. So
Sure.
the slope here of the between the p and the n type, can we also say that it starts to slope down at the beginning of the depletion region? And given this rule, does this mean that the electric field has a correlation to some degree on the width of the depletion region?
Oh yeah, absolutely. Absolutely. Yeah. The electric field, it turns out, we'll talk about this later, Melvin, is that the electric field is related to the width of the depletion region. When the width of the depletion region is very narrow, there's actually a very steep slope. And you have a very strong electric field.
But you can never have, let's say, a discontinuity there, though. So pretty much, would a discontinuity indicate like a infinite electric field?
Yeah,
So-
yeah,
so
that's
if you
right.
brought
A
'em-
discontinuity would imply an infinite electric field.
Okay, I got you. All right, thank you.
So that can't physically exist.
And that would mean the depletion region is pretty much non-existent at that case.
Yeah, the depletion region would limit towards zero.
So an inverse relationship between electric field and depletion region.
Depletion width. Yeah, that's right.
Yeah, depletion width. Okay, good.
Yeah, very good. So we talked about the electric field. So we had one rule of thumb there. Another rule of thumb is hole and electron concentration. Now, this is something that you already know. The closer the Fermi level is to the valence band, the more holes you have. And the closer the Fermi level is to the conduction band, the more electrons you have. Okay, so this is, in your p-type material, you have lots of holes. In your n-type material, you have lots of electrons. So I'm just drawing them out, drawing the holes and the electrons out like this. All right. And can anyone tell me why are the holes and electrons drawn in this manner? Why are they drawn lots of electrons at the bottom here, fewer electrons at the top?
Is it because the electron concentration and hole concentration is higher near the valence band and Fermi level?
That's right. Exactly.
And like the more you go farther, the less likelihood you can find carriers.
That's right. Exactly. That's basically the Fermi-Dirac statistics, right? We know like that the farther up you go from the Fermi level, there's less electron concentration. So most of the electrons are right at the edge of the conduction band. Thank you, Ellie. And similarly with the holes, most of the holes are very close to the valence band. The farther we go down, there's fewer and fewer holes that way. So that's why I've kind of like I've drawn them in like this simple triangular kind of format. So when we analyze this, now we have to think about, well, what can the electrons and holes do? Okay, this is how we use energy band diagrams to kind of predict and understand the behavior of carriers. So we can think about diffusion current. When we draw the energy band diagram, we can think about diffusion current. What's the definition? It's it's current that goes from high to low concentration. Right? Particles, holes, and electrons, they diffuse from high to low concentration. So when we look at this energy band diagram, we are recognizing the fact that there's a low electron concentration on this side, right? Because the Fermi level is very far away from the conduction band. So there's very few electrons here. But there's, a reasonable electron concentration here. So the electrons that have a high enough energy, they can actually diffuse over to this side. Okay. The electrons that have a lower energy, they encounter an energy barrier. All right. So this initially will look like, what is this? This doesn't make sense. But I'm going to try to explain why it's like this. Okay. We accept the fact that the electrons, some electrons have a higher energy than others, but there's just fewer electrons at a higher energy, at these higher energy states. The ones that are at higher energy states, they can diffuse over to this side. The way that we think about energy band diagrams, electrons like to go horizontally or down in energy band diagrams. What does that mean physically? Electrons will prefer to go to equivalent energy states or lower energy states. An electron won't go to higher energy states unless it is stimulated or unless it absorbs some kind of energy. Okay, so that's the first part of this diagram. That's why you see electrons moving in the horizontal direction. Okay, they can't move up. These electrons down here, they can't move up into the p side. Okay, so many of these electrons on the n side are not able to diffuse over to the p side. Only the highest energy ones can diffuse over. Okay, so this sort of illustrates what's happening with diffusion. Similar with holes. Okay, only the holes that happen to be at the lowest energy state can diffuse over into the end region. Remember, holes only can go horizontally, they can also go downwards. A hole moving from high to low energy is the equivalent of the hole moving from high to low energy is the equivalent of high to low energy is equivalent of an electron moving in the opposite direction. Okay, so now I want to introduce this idea of there are electrons that are making it over to the p side. So an electron diffuses over to this side, but remember there's also drift current. Drift current is the movement of electrons from high to low energy states due to an electric field. So if we refer back to our rule of thumb here, whenever there's a slope in the band diagram, that means there's an electric field. The electrons will move down the slope here onto the n side. Okay, that's illustrated by this arrow here, these two arrows here. Electrons drift down the slope. Holes drift up the slope. Now, again, I'm going to rehash why that is. An electron that's on the p side, it sees a slightly lower energy state right next to it. So the electron's like, okay, I will take that lower energy state. And then it finds an even lower energy state right next to that. So it'll go to this one, and then an even lower energy state after that. So it basically finds energy states and just continues on this way. And that is the representation of an electron going from higher to lower energy states, drifting from the p-type to the n-type region. Now a hole, the holes like to move up the slope, because remember, a hole moving up the slope is an equivalent of an electron moving down the slope. Okay, so holes moving up this way is considered the drift of holes from n-type to p-type. So now we can, again, just take a look at this again from a more holistic perspective. Some electrons here have enough energy to diffuse over directly to the other side, despite what we call this energy barrier. Okay. Other electrons can start diffusing over this side, but the energy barrier, they can be drifted back down this way. So there's actually the electrons can actually diffuse this way and then drift back over this way. And the electrons that have a high energy state, they end up diffusing all the way over, and then they can end up, they or a different electron can come drifting down like this. Okay, but either way, you see that there's a balance. There's a balance of diffusion current going from right to left, this upper arrow here, and then there's drift current going from left to right. And similar with holes here. They balance each other out. So that's the third and fourth things here. Now, the fifth bullet point is that this energy barrier determines the built-in potential of a diode. Okay, and some of you are not electrical engineers, so you may not know this, but those of you who are may recall, like what is a typical built-in potential of a diode?
0.7 volts.
About 0.7 volts, that's right. That's right. This is where that 0.7 volts comes from. So for those of you who are not electrical engineers, diodes, there we go. Let me just jump back to previous slide. So when we draw diodes like this, a diode is considered a device that conducts current in only one direction. It does not allow current flow in the opposite direction unless there's a secondary effect like reverse breakdown. Okay, but in circuits, we design circuits so that the diode only allows current going in one direction. But when there's a current going in that direction, there's, for silicon, there's roughly a 0.7 volt drop as you go from one side of the diode to the other. And this 0.7 volt drop is sometimes used as a shortcut by circuit designers to, it's a good rule of thumb. Like roughly when the diode is on, there'll be roughly a 0.7 volt drop across it. And that 0.7 volts is for silicon. For other materials, that number will change. And where it comes from is here. Okay, this slope in the band diagram represents an energy barrier for electrons to go this way and holes to go over to this side. Okay, questions? Questions? Okay. I like to show some diagrams from other books, other textbooks as well. Sometimes if my diagrams don't make as much sense and some other diagrams might make more sense, I like to give a little bit of that variety here. So this is the same type of situation kind of described by the Dmitriev textbook. So this is where you have your aligned Fermi levels, where the p-type and n-type materials, this is an n-type and then this is the p-type, they're not in contact yet. Just so people won't get confused, remember this is the n-type material and this is the p-type material. In the slides that you saw earlier, the p was on the left, the n was on the right. Okay, so the reason why this is kind of nice is because this shows carrier distributions, not in that triangular fashion that I showed you earlier, but it actually, it shows you more of like what the simulated carrier concentrations might look like. Okay, so you have your conduction band here, Fermi level right below it. You see that there's a lot of electrons represented by the black dots very close to the conduction band. There are fewer and fewer electrons the farther and farther you go up. And remember, in an n-type material, there are still some holes, very, very few holes. Okay, that's represented here. In the p-type material, you have many, many holes and very few electrons. This is before contact is established. So you have the Fermi levels here, but the bands have not done the band bending yet. Once equilibrium is established, okay, so actually before equilibrium is established, you can think about these, there could be electron diffusion here, electron drift here, but after equilibrium is established, this band becomes continuous. And this is what the bands look like. Very similar to the drawing that we had earlier, high electron concentration in the N region, lower concentration of electrons as you go to higher energies. This exchange here, these arrows, okay, these are the diffusion currents. And here you can see that electrons are trying to go in this direction, but they encounter this energy barrier. And due to that drift current, they end up just like drifting back down in this direction. Similarly, the holes, the high energy holes can, or the low energy holes can diffuse back and forth in this direction, and the lower energy ones strike the energy barrier and they end up returning. All right, so just another perspective on that. And this is, kind of a physical model, physical diagram that represents the fact that in an n-type material, you have lots of electrons, very few holes. In the p-type material, you have lots of holes, very few electrons. In the middle here, you form a depletion region. The n side has a positive charge. The p side has an effective negative charge. And you see the electric field is pointed from left to right in this diagram. In the diagrams that I showed you on previous slides, the electric field is pointed in the opposite direction because the p material is on the left, the n material is on the right. Okay. All right, so a little bit more on the built-in potential. This is an important quantity in determining the electrical performance of a diode. As I mentioned, for silicon, it's often typical doping. The built-in potential is like something like 0.7 volts. Okay, so we're actually going to determine that. So one way to find the built-in potential is by using the energy band diagram shown on the previous slide. And the second way is that you can derive it mathematically. So the first way is to use the energy band diagram. It turns out that this distance here in the energy band diagram is the built-in potential. This gives you the built-in potential. And I'll give you an example here. Like, well, for silicon, let's say, this distance here will typically be around 0.7 electron volts, somewhere around there. Okay, and 0.7 electron volts means that in the real world, the actual built-in potential of the diode will be 0.7 volts. Okay, now this is just a small but important detail here. The energy band diagrams show energy. So there's a difference in energy in the conduction band and the P side versus the conduction band on the N side. There's a difference in potential energy. Okay, but that in the real world, we can't measure potential energies, but we can measure voltages. Okay, the energy in electron volts is Q times the voltage in volts. Okay, so this is where the convenience of electron volts comes in. So this is the energy. So the energy is equal to 0.7 electron volts. Okay, so the energy is equal to Q times the voltage. So if we want to solve for the voltage, is equal to the energy divided by Q. Okay, don't confuse this E with the electric field, by the way. E in this case is energy divided by Q. So this is 0.7 EV divided by 1.6 times 10 to the negative 19 joules. But then you also have this conversion that 1.6 times 10 to the negative 19 electron volts is equal to 1 joule. So let me get that right, sorry. Let me just erase this. Okay, so the energy here is 0.7 electron volts. So 0.7 electron volts. If we want to convert that to joules into 0.7 electron volts, 1 electron volt is 1.6 times 10 to the negative 19 joules. Okay, so this is 0.7 electron volts times 1.6 times 10 to the negative 19. So 0.7 times 1.6 times 10 to the negative 19 divided by Q. And remember, Q is also 1.6 times 10 to the negative 19. So these two cancel, and you're left with 0.7 volts. Okay, that's the reason we use electron volts, by the way. Okay, there's a nice correspondence to the voltage and energy. The voltage is what we measure with our voltmeters in the real world, and 0.7 electron volts is what we represent on the energy band diagrams. Okay, again, the key concept here is the energy band diagrams represent energy. Okay, but we can derive the built-in potential from there. Okay, so what I'd like everyone to do, we have about 13 minutes left in class today. I would like everyone to use these two ways to find the built-in potential. Let me just go over this quickly in just a couple minutes, and then we can try both ways of calculating the built-in potential. So I'll cut to the chase here. There's a way that you can derive a formula for the built-in potential and it's just given by this very simple formula here. KT over Q, ln of Na Nd over Ni squared. So let's define what those are. Na is the p side doping. Okay. Nd is the n side doping. Ni is the intrinsic carrier concentration. And then KT over Q at 300 Kelvin, it's a rule of thumb, just remember that's 0.026 volts. Okay, don't forget the units there. KT over Q at 300K is 0.026 volts. KT on its own, which is what we used in module 3 quite a bit, KT is equal to 0.026 electron volts. All right, so this formula is a very quick and easy way to calculate the built-in potential based on the doping. And you can clearly see here that larger doping will give you a larger built-in potential, but it's a logarithmic relationship here. Okay, so where did this equation come from? It turns out you can derive this equation by just considering that the drift and diffusion currents are equal to zero at equilibrium, which is what we talked about, drift. So we're looking at the whole drift and the whole diffusion currents. The same derivation could also be applied to electrons, but we're just doing the holes now for simplicity. So the rationale here is that at steady state, the total hole current is equal to zero. The drift and diffusion components sum up to zero. Now we plug in, from what we learned in last module, the formula for drift current. Okay, this is this portion here. Q mu p times p represents the conductivity. Conductivity times the electric field is equal to the drift current. Okay, and this is from Fick's law, the diffusion current. Q times the diffusion coefficient times the concentration gradient. So from here, we set them. The sum of them are equal to zero. And then we come up with this just by moving things over to the other side. So at this point, we use the Einstein relationship. This Einstein relationship, remember, is D over mu equals KT over Q. And so here you can see that you have a D over mu, the inverse of a D over mu here. So that, using the Einstein relationship, becomes that KT over Q inverted. The other thing we do here is that the electric field is equal to the gradient of the voltage. Now, this is something that we haven't really talked about too much. This is an electromagnetics concept. Electric field is the spatial derivative of the voltage. So that's where this came from. And then you integrate both sides. You can see this is a differential equation. Both sides are with respect to x. So you have a dx here and a dx here. So, but the left side of the equation is voltage, and the right side of the equation is carrier concentration. So this is a little mathematical trick that you don't need to know for the purpose of this class. I'm just telling you that it's there. On the left side, when you do this, when you integrate this, you are integrating with respect to this. This is d dx of the voltage. So on this, you're integrating with respect to V. On the right side, you are integrating with respect to P, because it's dP dx. All right, so it's interesting. You can integrate the left and right sides by in two different ways. So you're integrating from the left side of the diode to the right side of the diode. So the voltage changes from Vp to Vn as you go from the left to the right side. The whole concentration changes from P sub P to P sub N as you go from the left to the right side. And so that's why you have that there. And then you, after you do the integration, you can simplify and there's just one other step here where you use NP equals NI squared to simplify this. And I'm obviously hand waving and leaving a lot of the details out just in the interest of time here, but you come up with this simple formula. Okay. Now what I'd like to do is just use the last 10 minutes of class or so to calculate the built-in potential of the diode in two ways. So I'd like half the class to calculate it using the energy band diagram, and the other half of the class to calculate it just using the simple formula. And I think, how about this? I mean, how about, oh, we only have 4 of us here left. How about Corey and Janan? If you could please try to do the calculation based on the energy band diagram, and Ali and Clayton, if you could just use the formula to calculate it. And what I'd like to do is give you 5 minutes to do your respective calculations, and then we can kind of go over. I want to see if the two if the two numbers that the two groups get will match with each other. Okay, and this is also just a good way to draw the energy band diagrams on your own and use the formulas. Okay, so again, Corey and Janan, draw the energy band diagrams for the PN junction and see if you can figure out the built-in potential that way. Ali and Clayton, just go ahead and use the simple formula to figure out the built-in potential, and we'll compare the results. So give you like 5 minutes to do that. Apologies, we'll end up just going a few minutes over class, and we'll end after this example. So I'll go ahead and mute myself now. Oh, if anyone needs me to go to a previous slide, if you don't have your PDFs on hand, then let me know. I'm happy to do that. So this is a step PN junction. The P side doping is 10 to the 18th. The N side doping is 5 times 10 to the 15th. Okay. I know we haven't had too much time to do it, but I just wanted to check on Corey and Janan if you have had enough time to draw out the energy band diagram.
I started drawing it, but I think I'm a little lost on this.
Okay, well, yeah, let's go through it together then. This will be a good exercise. So why don't we start with, here, I'll just draw out the different sides of the band diagram. And you can help me out with the parts that you have. So you start by drawing out the Fermi level like this. So this is the P side and then the N side. Just put down the dopings, 10 to the 18th and 5 times 10 to the 15th. N side, so this is the ND equals 5 times 10 to the 15th per centimeter cubed. Okay. So Corey or Janan, were you able to find the distance between EF and the conduction band? Or between EF and the intrinsic level?
That's what I was trying to calculate.
Oh, what was that, Janan? Sorry, I couldn't hear you.
I was calculating that, but I guess I got stuck. I was using the formula EF minus EI is equal to KT, natural log of N over NI.
Mm-hmm. Okay, yep.
And then, so for like NA, you would use that number, right?
That's right, that's right. So NA, yep, you're on the right track here. So NA over NI. Yep. So this will be 0.026 electron volts times the log of these two units are going to cancel. So it'll just be 10 to the 18th over 1.5 times 10 to the 10.
Yeah, so that's 0.972.
0.972 electron volts. Great. So let's see, Fermi level is above EI. 0.972. So this will be the EI on the P side of the junction. And if this is like 0.97 or 1.12 electron volts, will be a little bit larger than that. So our valence band will be down here, and the conduction band will be up here. Didn't get that right. 0.972. Are you sure that's? That seems like a large number here.
Oh wait, sorry. It's 0.468.
0.468. Okay,
Does that sound better?
I think that sounds about right. Yeah. Yeah, because the reason I'm saying this is because 0.972, the EF minus EI has to be less than the half the band gap. Otherwise, the Fermi level will end up above the conduction band.
Yeah, I think, yeah, it's 0.468.
0.468, great. Oops, there we go. 468 electron volts, good. Okay, so that's 0.468 there. Just for reference, this is 0.66 electron volts. This is about 0.66 electron volts. Why? Because the band gap of silicon is 1.12 electron volts. This is about half of that. So here's our conduction band here. So we drew the band diagram on the left side. So Corey, maybe you can help out with a similar process for the band diagram on the right side.
Sure. Yeah. So that equation would be.
Oh, I made a goof here. I'm sorry. Oh, geez, I'm sorry. This is the P. This is the P side. This is EF. It should be EI minus EF. I wrote it in the incorrect manner. Sorry. Okay, so we have to. Sorry about this. Janine, could you help me out here again? Could you tell me what that value was?
Yeah,
0.46.
Yeah, 0.468.
Okay. All right. So this is for a p-type semiconductor. Remember, this is Na over Ni. For a p-type semiconductor, we solve for EI minus EF. Okay, and sometimes we can even just denote this is on the P side of the junction. Some of the textbooks will have that. So EF minus EI is going to be 0.468 electron volts. So this distance here, this will be our EI. This is 0.468 electron volts. Sorry about that. Sorry about that confusion. Valence band will be down here. Remember, the Fermi level is close to the valence band in a p-type semiconductor. And then up here, this is the conduction band up here. Okay, and I'm not going to bother drawing in the 0.6, 0.66, and 0.66 here. Okay, this is your reference distance. The Fermi level is 0.468 electron volts below EI. Okay, let's go on to the N side of the junction right now. So in the N side of the junction, we calculate EF minus EI. And this is going to be equal to KT ln of ND over NI, 0.026 ln of 5 times 10 to the 15th, 1.5 times 10 to the 10. And then Corey, I think you had gotten a number for this, right?
Yeah, I found it to be 0.331 electron volts.
Okay. 331 electron volts. And so the next part we do is we draw the right side of the diagram. And we start with the EF minus EI. So that means the distance between EF and EI here is going to be 0.331 electron volts. And just to kind of draw it to scale a little bit, this was 0.468, so 0.331 will be a little bit less than that. Okay, so this is the EI on the P side. All right, and then we can draw out the conduction band. Okay, remember the distance between the conduction band and the intrinsic band is going to be about 0.66. So 0.331 is about the same equidistant from, close to about half the distance between EI and EC. So I'm just kind of like thinking about the scale in my head as I draw this. And of course here, this is the valence band. And this time I'm just going to actually write out the 0.66 just so you can see the sense of scale on this band diagram. 0.66 electron volts, 0.66 electron volts to half the band gap. Okay, now the next part here where we try to figure out the built-in potential and draw the full energy band diagram, the first thing we have to do is connect the bands like this. So the conduction band bends like that. The valence band bends like this. And the intrinsic level also bends. It looks something like this. Okay, so we connected them together. So this is what our band diagram looks like. Now, I know we're over on time here. I'm sorry about that. So this is what we want to find out. We want to find out is what is this energy barrier here? What is this distance here? Because that's going to tell us the built-in potential. So I want to see if someone can just look at this diagram and tell me what that number is going to be, or how we can find it.
It'll be the 0.468 plus the 0.331.
Yeah, you got it. This is 0.468 plus 0.331. And what does that come out to?
0.799.
0.799 electron volts. Well, let's just say this is 0.8 electron volts. So that's the main thing I wanted you all to see by going through this exercise, is that this distance here, if we label this A, and this distance here, we label this B, and you know how to calculate those. This is A, this is B. The energy barrier, which allows you to calculate the built-in potential, is just A plus B. Okay, so this gives us an energy barrier of 0.8 electron volts. And so this implies that the VO is equal to 0.8 volts. That's the built-in potential for this particular diode. Okay, and Ali and Clayton, did you guys get similar numbers when you just plugged in the formula there?
Yeah, I got exactly the same.
All right, so using the basic formula, VO is equal to KT over Q, ln of NA ND over NI squared. This will be 0.026 volts times ln of 10 to the 18th times 5 times 10 to the 15th. And this will be over 1.5 times 10 to the 10 squared. Okay, and keep in mind, this is over centimeters cubed, this is over centimeters cubed, this is over centimeters cubed, and this is squared. So all the units here will cancel. And this will give you, if you do the math here, it'll give you about 0.8 volts. All right, so both ways you do it, whichever way makes more sense to you. This is obviously just using the formulaic approach is the faster way to do it. But I want you, the last thing I want to show you real quick is how these two, you can just derive this very easily. If this is A on the left and B is on the right, then the built-in potential is equal to A plus B. Okay, so this is KT ln of NA over NI plus KT ln of ND over NI. Okay, and just a few lines of math, we can show that it's exactly equal to the same formula. So this becomes KT ln of NA over NI plus ln of ND over NI. Right, and when natural logs add, when you add natural logs together, the sum of them becomes one natural log of the product of whatever is inside. So this becomes KT ln of NA ND over NI squared. Okay, so you can see that the formula is exactly the same as what you see here. These two formulas are identical. All right, so thanks for the extra 10 minutes. Appreciate it again. That now you know how to calculate built-in potentials for a diode, how to draw the energy band diagram. Next time in class, we're going to go into more details of the depletion region, and we're actually going to solve for the charge densities, the electric fields, and so on. A lot more details about the physics of the depletion region we'll go into next time. And then we'll get into forward and reverse bias diode, what happens when you apply a voltage, a forward or reverse voltage to the diode. Okay, thanks everyone. Thanks for staying extra, and I'll see you all on Wednesday. So reminder that your project outlines, for those of you who need a little bit extra time, that's no problem, but try to get your project outlines in by Wednesday if possible. And the second group, if you need a few extra days, that's also fine. Let me know.
Thanks.
Okay, thanks everyone. Talk to you soon. See you soon.